Okay, so imagine this for a moment. A cold so extreme that motion itself almost disappears. Not the cold of ice, not the cold of a polar night, not even the cold of space between stars. A physical boundary the universe seems to obey like an absolute law. A point where atoms nearly stop moving, where time feels frozen, where matter enters states that defy everything we experience in daily life. That limit is called absolute zero. And the most unsettling part, we will never reach it. Number 8, the mathematical limit of cold. Absolute zero is the lowest possible temperature allowed by the laws of physics. On the Kelvin scale, it exists at 0 Kelvin, equivalent to negative 273.15 degrees Celsius. It isn't just very cold, it is the point where thermal energy reaches its minimal possible value. To understand how extreme that is, consider this. Liquid nitrogen, one of the coldest substances commonly used in laboratories, boils at negative 196 degrees Celsius. Absolute zero is still 77 degrees colder than that. At these temperatures, matter behaves in strange ways. Atoms barely move, quantum effects dominate. Particles begin overlapping in ways impossible at higher temperatures. In 1848, William Thomson, later known as Lord Kelvin, formalized this temperature scale. He discovered something remarkable. There is a lower absolute limit to temperature, but no upper one. You can always heat something more. The cores of stars reach billions of degrees, but downward, there is a wall, a floor the universe refuses to cross. Number 7. Space is not empty of temperature. For a long time, people assumed deep space must be the coldest place possible. After all, it's dark, silent, almost empty, but even the vacuum has temperature. Far from stars and galaxies, the universe averages about 2.7 Kelvin. That's approximately negative 270.45 degrees Celsius. Incredibly cold, but not absolute zero. That residual heat comes from something ancient. The cosmic microwave background radiation, the thermal echo of the Big Bang. Nearly 14 billion years ago, the universe began in an incomprehensibly hot state. As it expanded, it cooled, but that original radiation never fully disappeared. It stretched, it weakened, it cooled with expansion. Today, it fills all of space as a faint microwave glow. Because of this radiation, the universe has never reached absolute zero, and as long as it exists, it never will. But there are places that get even colder. Number 6, the coldest natural place in the universe. In certain dark nebulae, vast clouds of gas and dust where stars are born, temperatures can drop to around 10 Kelvin. That's minus 263 degrees Celsius. These are regions where energy is scarce and heat travels slowly across immense distances. But one object goes even further. The Boomerang Nebula, located about 5,000 light-years away in the constellation Centaurus, is the coldest naturally known place in the universe. It reaches 1 Kelvin, just 1 degree above absolute zero. How? It's formed by a dying star ejecting its outer layers at extreme speeds. As gas expands rapidly, it cools dramatically, a process known as adiabatic expansion. Like when you spray an aerosol can and feel cold gas escaping. Except here, the gas is expanding at 600,000 kilometers per hour. The cooling is so intense that temporarily it becomes colder than the surrounding cosmic background radiation. For a brief cosmic moment, it is colder than the universe itself. And yet, still above absolute zero. Number 5. The coldest places are on Earth. The most extreme cold ever created does not exist in space. It exists in laboratories on Earth. Scientists have cooled atoms to millionths, even billionths of a degree above absolute zero. They don't use ice, they use lasers. The method is called laser cooling or Doppler cooling. Temperature at the atomic level is simply motion. The faster atoms move, the hotter they are. So physicists aim laser light at atoms moving towards them. Each photon acts like a tiny brake, reducing the atom's velocity. It's like slowing a car by throwing microscopic tennis balls at it from the front. As atoms slow, their temperature drops to nano Kelvin levels, billionths of a degree above zero. In 1995, physicists Eric Cornell, Y.M. Wieman, and Wolfgang Ketterle achieved a breakthrough. They cooled rubidium atoms to about 170 nano-Kelvin. At that temperature, matter entered a new state, the Bose-Einstein condensate. In this state, thousands or millions of atoms behave as a single quantum entity. Individual identity disappears. They merge into one coherent wave. Einstein predicted this in 1924, based on work by Indian physicist Satyendra Nath Bose. It took 70 years to observe, and yet absolute zero remained untouched. Number 4. The third law of thermodynamics. Why can't we reach it? Because of a fundamental rule of physics. The third law of thermodynamics, formulated by Walther Nernst in 1906, states it is impossible to reach absolute zero through a finite number of physical processes. You can get closer, but never all the way. Each step towards zero requires more energy extraction, more time, more precision. The closer you get, the harder it becomes. It's like walking towards the horizon. It always stays ahead. But there's something even deeper. Even if you could remove all thermal energy, quantum mechanics prevents particles from being completely still. There is something called zero-point energy, a minimum vibrational energy that cannot be removed. This comes directly from Heisenberg's uncertainty principle. You cannot know both the exact position and exact momentum of a particle simultaneously. If an atom were perfectly motionless, its momentum would be exactly zero, but then its position would become infinitely uncertain. That violates quantum rules. So even at theoretical absolute zero, motion never fully disappears.
Number 3. Absolute zero and the fate of the universe. This makes absolute zero almost philosophical, not a destination, but a boundary. Cosmologists predict that trillions upon trillions of years from now, the universe may enter a state called heat death. Stars will burn out. Galaxies will drift so far apart that light from one will never reach another. Matter will decay. Black holes will slowly evaporate via Hawking radiation. Eventually, only darkness and extreme cold may remain. Will the universe reach absolute zero then? No. Zero-point energy will still exist. Quantum fluctuations will still appear in empty space. Virtual particles will still briefly emerge and vanish. The universe may approach perfect cold, but it will never freeze completely. Absolute zero is an asymptote, an unreachable limit. Number 2. Human records in the search for cold. Even knowing it's impossible, humans continue to push closer. In 2003, researchers at MIT cooled sodium atoms to 450 picokelvins. That's 0.00000000045 Kelvin. The difference between that and absolute zero is smaller than the difference between absolute zero and deep space. In 2021, German scientists working with the Cold Atom Lab aboard the International Space Station achieved temperatures as low as 38 picokelvins. Why perform the experiment in space? Because microgravity allows atoms to remain suspended longer. That extended time enables deeper cooling. The coldest objects ever created by humanity were made in orbit. The place we once assumed would naturally be the coldest. It turns out
The coldest spots in the universe are artificial.
Number 1. Why absolute zero matters. Why chase something we know is unreachable? Because near that limit, physics changes. Bose-Einstein condensates allow us to observe quantum behavior on visible scales. Superconductivity, materials conducting electricity without resistance, becomes more accessible. These discoveries may revolutionize quantum computing. They may allow clocks so precise they lose less than a second over billions of years. Absolute zero isn't just a number. It's a gateway. Each fraction of a degree closer reveals new layers of reality. Absolute zero reminds us that the universe has boundaries. We cannot travel faster than light. We cannot cool below 0 Kelvin. We cannot measure position and momentum with infinite precision. The cosmos operates under absolute constraints. Yet within those limits, there is infinite room for discovery. Every time we approach a boundary, we find the universe stranger than we imagined. And remember, the universe doesn't reveal its secrets to those who rush. It reveals them to those who know how to look. Subscribe and keep listening to the silence.